Today we are going to do our last section in Chapter 5, the last of the types of problems that we're going to do in which we use derivatives to help us do something else. In this particular section, we're going to have all word problems. And these word problems are going to ask for us to find a minimum or a maximum value. Okay, so what I have written down on this very first page is a general strategy that I'm going to follow when answering all of our word problems. First of all, we're going to draw a picture. And then we're going to have to write down two equations, a primary equation and a secondary equation. The primary equation will involve what you're trying to minimize or maximize. And then the secondary equation is also known as a constraint equation. The second equation that we write down will be a second equation relating variables in a very specific way. We're going to solve this and eliminate one of the variables from our primary equation. So that's the goal with the secondary equation, is to try to use it to eliminate a variable. Then what we can do is take the derivative and find critical numbers, because critical numbers are where maximums and minimums happen. And we can't take the derivative until we have the equation in terms of only one variable. So we're going to find the critical numbers and then figure out if we have a max or a min and answer the question. Okay, so we're going to do 5 examples. The first one is very simple, and it requires no picture. So it says find two numbers. I'm going to call the first number x, and the second number is going to be called y. The product of x and y is 42. Now I want to their sum to be a minimum. So I'm going to write an equation called S for sum, and sum equals x plus y. So this is my primary, because this is the equation that I want to have the minimum or the maximum of. Now, if you look at S, if I take the derivative of S, I can't do that because I have two different letters, and which letter am I taking the derivative of? It's unsure. So we use the secondary equation, which is the constraint. So there has to be some sort of relationship between the two quantities. And in this one, their product has to be 42. I'm going to solve for y in the constraint. Then I'm going to rewrite my primary and replace y with what it is in our constraint. And now notice S is a function of x only. And so let me write this with a power. And I can take the derivative of this and set it equal to 0 to find critical points, which are where maxes and mins should be. And that's the whole idea of this. If I get a common denominator here, then my critical points are x squared equals, where x squared equals 42 and where x squared equals 0. So if one of them is 0, or at plus or minus square root of 42, which is 42. No, yeah, that's it. So x equals square root of 42, plus or minus. And the sum of the numbers has to be a minimum. So let's see here. If y is 42, or if x is 42, then going back over here to my primary equation, then y would equal 42 divided by square root of 42, or square root of 42. And x cannot be 0, can it? So one of the parts of the directions said to only use the numbers that make sense in terms of the problem. And it doesn't make sense for x equals 0, because if x equals 0, then I would have a product of 0, not a product of 42. So y equals square root of 42. And notice if x is negative square root of 42, then y equals 42 divided by negative square root of 42, or negative radical 42. And so either x equals radical 42 and y equals radical 42. And so x plus y would equal 2 radical 42. Or x equals negative radical 42 and y equals negative radical 42, and x plus y is negative 2 radical 42. And so you can see that this is the smaller one, so this is where I have the minimum. Okay, so this is kind of a silly math type question. And my next example here, I have sort of a real world application. I have a farmer who wants to put up a rectangular fence. He's putting this fence beside a barn. So here's my barn. And I'm going to put in a rectangular fence. So he's going to do this wisely. I'm going to only have fencing on 3 sides here. So one of the barn itself will provide enclosure. Then I need to put a divider fence perpendicular to the barn. Maybe he wants to keep the boys and the girls separate. But we're going to put up another fence perpendicular to the barn that divides my pen. He has 60 feet of fencing. That's important. What are the dimensions of the pen that will give him the most area fenced in? So notice my area is what I want to maximize. So in terms of my picture, I'm going to introduce some variables. I don't know how long to make this perpendicular section. Notice that all 3 should be the same length if it's rectangular. And I don't know how long to make the long section. And so I have 2 variables that I need to figure out. Now, my primary equation will involve area because that's what I want to maximize. So area is the product of x times y here. My secondary equation is going to use the fact that I have 60 feet of fencing. So that's my constraint. Farmer Joe can't build the biggest pen possible because he only has 60 feet of fencing that he's going to use. And so I need to set up an equation with 60 feet of fencing. You can see I've drawn in my fence. So how much fence is in this picture? Well, I have 3 perpendicular portions that are x long each. Plus I have this long portion that I have described as y long. And so this has to be 60. Okay, so I'm going to solve this equation for y because that's easier. Y is 60 minus 3x. So this was my secondary equation, and it's a constraint. Y must be 60 minus 3x. So now I go over here and I'm going to replace that y. And now I have an area formula in terms of x only. Once you've gotten to this part, we get to do calculus. Well, let me distribute this x first. So I'm going to do calculus. I'm going to take this derivative, and I'm finding critical points here. So I'm going to set the derivative equal to 0 and solve for x. X is 10. So 10, working with x equals 10 will give me a critical point or a maximum here. And so if x is 10, I can go back over to my secondary equation and see that y would be 60 minus 3 times 10, or 30. And now let's go answer the question asked, what is the maximum area and what are the dimensions? So he should go, the dimensions are 10 feet by 30 feet, and the maximum area is 300 square feet. And we're done. That's the answer to the question. All right, next example. We have another sort of real-world example. I have a rectangular box. It's open. The word open here means no lid. It's got a square base, and I have 48 square feet of material with which to make the box. What dimensions will result in the box with the largest possible volume? Step 1, draw a picture. I'm going to draw a picture of a box. It is rectangular, but the base is square. So imagine one of those short, cute little, almost cubicle tissue boxes, but they're not cubes because they're taller, but their bases are square. Okay, and since this is open and it has no lid, I'm going to draw a little arrow here to remind myself that I can throw stuff in it. Okay, and let's see here. The base is square, so let me call the base x by x, and let's call the height of this y. All right, so there's a very accurate picture for this problem. Let's write down our primary equation. The primary equation should deal with what? Well, what do I want to maximize? What do I want the largest of? I want the largest volume. And so therefore, my primary equation is the volume of this box. So the volume of the box is length times width times height. In this example, that will be x times x times y. This is what I want to maximize, so I want to take the derivative and set it equal to 0 to find critical points, which are where maximums happen. My problem is that I have this equation in terms of two letters, both x and y, so I have to eliminate one. All right, so let's find our secondary equation, which is a constraint equation. There's one other number up here. It says 48 square feet of material. I have 48 square feet of material. And so that would describe my surface area. So our constraint is that we only have 48 square feet of material with which to make our box. And so if you think about it, we're making the box out of material, and so the material are these four lateral surfaces and then the base. And this is a surface area of the box is what the material is. The material makes the surface area of the box. So let's talk about the surface area of this box in question. I have four lateral surfaces, which are x by y area, plus I have one base, not the top though, which is x by x. And that's the total amount of surface area of my box. Assuming I can cut this perfectly, that could be, that can add up to 48 square feet of material. All right, so let's solve this constraint equation for one of my variables, either x or y. As you can see, it's easiest to solve for y because I don't have a squared and a non-squared y. So when you solve for y, you get 48 minus x squared over 4x. Let's go ahead and plug this in over into our volume equation, and now my volume is in terms of x only. So I have x squared, 48 minus x squared over 4x. Now, before we take the derivative of this, you want to simplify a little bit. Okay, so the way this works is this is an x squared over 1. And so you can cancel one of the x's here. And then you have this 4, it's like a 1/4. And there's that x still, and that needs distributed to the 48 minus x squared. That will be the easiest thing, it'll be best to distribute that before we take the derivative. So that's going to be 12x minus 1/4 x to the third. And so let's take the derivative. 12 minus 3/4 x squared. We're going to set this equal to 0 and solve for x. So that's when 12 is 3/4 x squared. 16 is x squared. So x equals technically plus or minus 4, but let's be realistic. X is the dimension of a box. It's not going to be negative. So x is 4. If x is 4, let's go back over here to my constraint here. Then y would be 48 minus 16 over 16. That's 32 over 16. So this is 2. And so the dimensions of my box are 4 by 4 by 2. What's the question? Yeah, the dimensions. And so my answer is 4 by 4 by 2. I think this is feet. And we're done. All right, we've got, I think, 2 more examples. In this example, I have another container. This container is not rectangular. It is a right circular cylinder. So I'm going to draw myself. Right just means it's not tilting anywhere. Perfectly straight up and down. Again, this one has no top, so we want to think we can throw stuff in there. It has a surface area of 3 pi square feet. What height h and base radius r will maximize the volume? So I want to find the biggest volume of the cylinder. The volume of a cylinder is pi r squared h. I have to eliminate either r or h. Look at the information given. We have a constraint in which our surface area can only be 3 pi square feet. So let's talk about the surface area of this thing. I have a lateral is just the side. I have this lateral surface here that makes up the edges of it. And the edges of it, if I took a pair of scissors and I cut up one side, and then I could unroll this lateral side, and when I unrolled it and flattened it out, eventually I would get a rectangle. And this rectangle would have a height of h, and the base length here would be the circumference of the bottom circle. Circumference is 2 pi r. And so this surface area, the lateral surface area, is 2 pi rh. Plus, I have the base pi r squared area. It's open, so I don't have a top. So that's my surface area, and that is supposed to be 3 pi square feet. So this equals 3 pi. 3 pi. 2 pi rh plus pi r squared. Okay, obviously, well, to me, because we have an r here and an r here, it's easiest to solve this guy for h. So let's solve this for h. Let's cancel the pi's. Pi's are everywhere. And so I factored out a pi on the right side and then divided by pi. So 3 minus r squared divided by 2r, that's going to be h. Let's go replace the h in my volume formula with what I just got there, 3 minus r squared over 2r. And again, we want to simplify this before we take the derivative. So I'm going to think about this as pi r squared, 3 minus r squared over 2r, because this is over 1. And r will cancel. And so I have pi over 2r. That gets distributed to my 3 minus r squared. So this is 3 pi over 2r minus pi over 2r to the third. Now this one is easy to take the derivative of. So I'm going to take the derivative. I get 3 pi over 2 minus 3 pi over 2r squared. We're going to set this equal to 0. So this is going to happen if r squared is plus or minus 1, or really only 1 makes sense there. So r equals 1 is my radius for the maximum volume. Come over here to find what h would be. H would be 3 minus 1 over 2, which is 1. So h is 1. And let's make sure we're answering our question. What are the height and base radius? So 1 foot and 1 foot. Okay, we're on the last question. Now we're going back to a very mathy type of example. Well, what's happening here is I have a region, a closed region bounded by some graphs. So I'm going to graph. I'm in the first quadrant here, and I just know that from experience. So here's the y-axis, here's the x-axis, and then I have this cubic 8 minus x cubed. Okay, so if x is 0, y is 8, and if x is 2, y is 0. If x is 1, y is 7. This is a cubic function flipped upside down. Okay, and so you can see here's my region right here, R. Now, what we're doing with this region is we are inscribing a rectangle inside of it. Inscribing a rectangle inside of it. So to inscribe a rectangle, that means that the corners are going to, we have to put the biggest rectangle in that we can. And so the corner is going to have to touch that curve. So maybe this green rectangle will have the most area. It certainly looks like more area than, say, this rectangle here, which is also inscribed, right? It's also inscribed. Or perhaps this blue rectangle has more area. It's skinnier, but it's a lot taller. So the question is, how do I inscribe this rectangle to get the biggest area? Okay, so I'm just going to work off the green one. I'm going to pretend the green one's it. It has dimensions, let's call them x by y. And that makes sense because this point on the graph, we would call it xy. But I'm not specifying what x is or what y is. So that means the area of my rectangle is x times y. Okay, so that's my primary equation because this is what I want to maximize. Let's talk about the secondary equation. There needs to be some sort of relationship between x and y so I can eliminate one of those variables. And there is. This point xy on the curve here is described by that relationship right there. And so you don't even have to do any additional work for this. You just have to recognize that you already have a secondary equation. And so my area is x by 8 minus x, 8 minus x cubed. So we distribute x, take the derivative, 8 minus 4x to the third, set this equal to 0 to find the critical points because critical points are where maxes and mins occur. So this happens when x to the third is 2. And so x is going to be the cube root of 2. And so if x is cube root of 2, what is y? I have to go back to this equation right here. Y would be 8 minus cube root of 2 cubed, which is 8 minus 2, or 6. So it turns out that a rectangle with cube root of 2 by 6 gives me the maximum area. Except, what did it ask for? Find the dimensions. So cube root of 2 by 6. That will give me the maximum area. And we are all done.